In this video, we're going to be talking about direct and inverse variation, and specifically we're going to be talking about where we use these and how we use these as tools to solve application problems. Direct variation means that the ratio between two variables is a constant, and inverse variation means the product of two variables is a constant. So examples of direct variation are the ratio of feet to inches, that there's 12 inches for every 1 foot. A scale on a map, how many cookies I can make with how much dough I have. Inverse variation is a little less intuitive. So direct variation, one thing increases, the other thing increases. Inverse variation is it's a little bit more off kilter. So an example is a pulley system or a gear or lever arms, or the time it would take for people to wash windows with the number of people washing the windows. So as one thing increases, another thing decreases by a decreasing amount. So let's talk about equations. Direct variation, since the ratio of two variables is a constant, we could set that up as a proportion. The ratio of y to x is the ratio of y2 to x2. In inverse variation, on the other hand, it doesn't quite work that way. Since the product of two variables is constant, it's better to write it like this: x1 times y1 equals x2 times y2. Jumping back to direct variation, since the ratio of these two variables is constant and we can set it up as a proportion, another way to write this is by recognizing that this ratio is constant, we just take the ratio and set it equal to a constant. That's what this k is. It's a constant of proportionality or a constant of variation. If we take this y divided by x equals k, and we just multiply both sides by x, we transform this equation into y equals kx. This is a pretty useful form for direct variation. For inverse variation, since the product is constant, we can write x times y equals k. If we solved for y, we just divide both sides by x, and we end up with y equals k divided by x. So this is kind of our most standard inverse variation equation. So the question is what would this look like if we graphed it? And please ignore our book and other books. Direct variation, if you recall, that's the form y equals k times x if we wrote it with a constant. This is a linear form. This is a little different than y equals mx plus b, because y equals mx plus b, you can change your y-intercept, you could have a negative slope, and with direct variation, it's always an increasing value. Inverse variation, this is the form y equals k divided by x, gets us a much crazier graph. So some of you might be familiar with this graph already. This might be the first time you're seeing it. I would encourage you to sketch out a table of values and figure out how this graph works. So start with some negative, maybe try and throw in a 0, and then go positive. The problem is when you get to 0, you would have y equals some number divided by 0. That's undefined. And so at this point, it's helpful for your x values if you plug in things like -1/2, -1/3, -1/4, and do the same thing on the positive side. And that will get you this graph right here. All right, let's do an actual problem. So direct variation. Before we even start this, I want to write down some of the things I know about direct variation. I know that the ratio is constant, and so I can think of this as y1 over x1 equals y2 over x2. I also, if I like equations more than proportions, can think of this as y equals some constant times x. This problem says that Hooke's law basically states that the force needed to extend or compress a spring varies directly with the distance of that deformation. If a 22, let me highlight some of this. If a 22 kilogram weight pulls a spring down by 100 centimeters, so there's one situation, how far down would a 16 kilogram weight pull the spring? So what we have here is we have a situation that we know, which is that 22 kilograms pulls at 100 centimeters, and a situation that we don't know how far, with 16 kilograms. And I skipped right over the fact that this is direct variation. I know it's direct variation because the problem literally says varies directly. Sometimes we might not have that clue, but in this case we do. I think I'm going to set this up with proportions. So it doesn't matter if I put the weight on top and the distance on the bottom, or vice versa, just as long as I'm consistent. So I'm going to put the weight on top. So 22 kilograms per 100 centimeters. So this is basically my y1 over x1 equals, now weight was on top, which means 16 kilograms has to go in the numerator. And then how far down, that's what I don't know. Let's use d instead of x, d for distance. So this is y1 over x1 equals y2 over x2. Now that we have a proportion, we can cross multiply. 22d equals 1,600. Divide both sides by 22. Got d equals 72.72 repeating. And this distance should be in centimeters. I didn't say anything about significant figures here. I probably should have. Since this distance has 3 significant figures, we'll pretend it's 100 centimeters. Well, let's write this answer to 3 significant figures. So that's 72.7 centimeters. Another example of direct variation has to do with hydraulic press. And so hydraulic press, there's a mechanical advantage, and that mechanical advantage is equal to the ratio of the force of the large piston. So there's our large piston. So the force exerted by this large piston divided by the force exerted on the small piston. Fs is force on small piston. And this is also equal to the radius of the large piston squared divided by the radius of the small piston squared. So there's our proportion right there. Force of the large divided by force of the small equals the radius of the large squared divided by the radius of the small squared. So this is a ratio. Let's do a problem. Let's say that a force of 8,100 pounds is exerted by a piston of radius 30 inches of a hydraulic press. All right, so there's one situation. What force was applied to its piston with a radius of 3 inches? So again, we have 2 situations here. We have one situation where we know both parts and one situation where we're missing a piece. I know that hydraulic press work with direct variation, operate as direct variation, and we have our setup right there. So what I've highlighted in orange is the large piston, and I know that because the radius is 30 inches. What I've highlighted in yellow is the small piston. So the force of the large piston is 8,100 The force of the small piston, that's what we don't know. The radius of the large piston is 30 inches, so this is going to be 30 squared, divided by the radius of the small piston, which is 3, so that's 3 squared. Remember that you cannot simply simplify out a squared. We have to figure out what that is. So this is 8,100 over F equals 900 divided by 9. Now, if we wanted to, we could simplify that fraction. Let's go ahead and do that, just to make the math a little easier. So I know that 9 goes into 9 once, and 9 goes into 900 100 times. And so our fraction, our ratio, becomes 8,100 over F equals 100 over 1. And that's easier for me to cross multiply without a calculator. 100F equals 8,100. Divide both sides by 100. And we've got the force exerted on the small piston is 81. And that is 81 pounds. Inverse variation. And I know this is a longer video. Pulleys, gears, and levers, or seesaws, all operate as inverse variation. Remember that inverse variation, the product is constant. x1, y1 equals x2, y2. So let's do a problem. A large gear with 80 teeth, turning at a rate of 150 revolutions per minute, turns a small gear, so we have situation 1, large gear, 80 teeth, 150 RPM, and this turns a small gear with 12 teeth. At how many RPM does the small gear turn? So, similar to direct variation problems, we have a situation we know and then a situation we know part of, but how we're setting these up is very different. And this is very important to understand the form that the equation is taking, understand the mathematical relationship behind what's going on. So since I know that this is an inverse variation, I am now going to take the product of those numbers in my first situation and set it equal to the product of numbers in my second situation. That looks like 80 times 150 equals 12. We'll use X this time for the RPM of the small gear. So multiplying this out, 80 times 150, we have 12,000 equals 12x. Divide both sides by 12 and get 1,000 equals x. So that smaller gear with a lot fewer teeth is flying. It is spinning its little heart out at 1,000 revolutions per minute. Okay, so just to hit it home, inverse variations follow so frequently the same pattern. Product of two elements in thing 1 equal the product of the same two elements in thing 2. This is true with pulleys. The diameter of a first pulley times the revolutions per minute equals the diameter of a second pulley times revolutions per minute. The number of teeth in a first gear times the revolutions per minute equals the same thing in the second gear. The force on side A times the distance from the fulcrum or tipping point of the lever equals the force needed to be exerted on side B times the distance from that fulcrum. I do expect you to be able to identify these problems as inverse variation and to use the appropriate form, setting it up as a product, not a ratio. One more problem. A 1,200 gram mass is placed 72 centimeters from the fulcrum of a lever. So that's the center of a seesaw. How far from the fulcrum, so we're looking for the distance, is a 1,350 gram mass that balances it. So just thinking this through, I have two kids, an older boy and a younger girl, and my boy he's heavier than my daughter. And if he sat on the end of a seesaw, if they both sat on the end of a seesaw, it would tip down in his favor. And so to balance it, he has to move in closer to the center. So if he sits closer to the center of the seesaw, my two kids can actually balance on the seesaw. All right, so what we have here is 1,200 gram mass times 72 centimeters equals 1,350 gram mass times x centimeters. So we have the product of situation 1 equals the product of situation 2. To solve this, I multiply these two together and divide by 1350. 64 equals x. Just as I hope that we would expect, a heavier mass needs to be closer to the center of the fulcrum in order to balance a lighter mass that is further away. Thank you.